is for you. Okay. Now the first gas property I want to talk about it is the equation of state. Okay. My first question is, have you studied about equation of state before? PV is equal to nRT.
Yes, we do.
Yes.
Okay. What is it?
It is the equation of ideal gas.
Okay. Why we have it? Why we have this equation? Anyone? There are 2 or 3 multiple uses of this equation. A very good use actually. Anyone? Okay, what is the benefit of this equation? I tell you, for me, this equation, it saved my master's degree. It served that much for me personally, that equation. And I was in a big mess in my final one. They were, if I would not be able to solve, I might lose my degree. But then Boyle's law, Charles' law, and ideal gas law, especially mainly Boyle's law and Charles' law, they helped me to figure out, solve my problem. And I didn't tell anyone how. I will tell you the story. But first I want to know what is the equation of state? Okay, so let me talk about it. What is it? From my point of view, how I think about the equation of state. First of all, we can say that the equation of state basically describes the state of a fluid. Okay, let's say you have the gas reservoir, or you have the oil reservoir. Okay, one behavior is physical, right in front of you. Okay, but you cannot do the experiment again and again. For example, now somebody asks you to get me the volume, because as you know, volume is depending upon pressure and temperature. If you change the pressure, volume will change, right? You agree all with me with that? Okay. You agree with me that the pressure and temperature changes the volume? Anyone, please?
Yes.
Yeah. Okay. Pressure and temperature changes the volume of the fluid. If you increase the pressure, volume will decrease. Okay. If you increase the pressure, the volume will decrease. This is the first thing. Okay. Now, if I ask you, okay, I have a fluid, okay, and its pressure is 4000 psi, okay, and its temperature is 100 degrees centigrade. Now I want to reduce the pressure from 4000 to 1000, each in the step of 10. Let's say 3990. What is the volume? 3980. What is the volume? 3970. What is the volume? Of course, you can do it physically. How much time it will take for you? You have high pressure vessel container. You can change the pressure physically. How much time it take for you?
1 day.
1 day. Now leave that. Go to the Microsoft Excel. Okay. Use this equation and do some small calculation. Put the pressure, put the temperature, put the constants. You will get it maybe in few minutes. All of it. That's the benefit of this equation. That you have the physical. If you go for the physical thing, it will take a lot of time calculate, and sometimes you have to do the pressure, volume, temp. Reservoir fluid is all about pressure, volume, and temperature, and you have to do it a lot in the other equations. You have to use it a lot in management of oil reservoirs. These kind of calculations. So if you go physically again and again, it will take 1 day at least, as you said. But if you have equation, you can do it. This is the first benefit of it. It saves your time. Using those equations, you can really actually get the volume in very soon, as soon as possible. So basically this equation of state describes connecting the pressure, volume, and temperature. How is the temperature affecting on the volume, or how is the temperature affecting on the pressure, or how the volume is affecting on the temperature or pressure. So basically it is connecting pressure, volume, and temperature. That's what it is doing. It's very important because we need it for reservoir fluids, reservoir engineering calculation. This one, when I will do the 1 day course, you will see the use of them there. Okay. This is the first thing. Now, the second benefit of it, as we discussed earlier, that physically you can work on the rig. You know there's a bed, there's drill pipe, drill collar, drill string, hoisting, rotating. It's all physical. In production system, there's a Christmas tree, there's a separator, there are pipes, completion, this, that, well, walls, this wall, that wall, there's a pressure loss. Everything is right in front of you. Both are fine, easy to work. But reservoir is deep, is down. You cannot go there, touch the reservoir. You cannot actually see the reservoir. You cannot do anything with it. Okay, all you can do is imagination. Imagination and calculations. Calculation, imagination, calculation, imagination. This is all is reservoir engineering. So what we actually do, we create the mathematical models similar to the reservoir based on our imagination, and we put them in the softwares and we do our calculations. Okay, so for that, definitely when you want to simulate your reservoir, you need a fluid. What you will simulate? You need a fluid for that. And how you can bring that fluid condition from physical inside your computer. So you need an equation that can really convert that physical thing into the mathematical thing so that you can play with that fluid. So for me, if you put the properties, it will definitely, talk about the fluid, which is actually physical, but here you can get the numbers, in numbers, those values. So actually the mathematical thing and physical things, they both are connected. So in order to convert that physical thing into the mathematical form so that we can perform the calculation, we need an equation. So that's why we have this equation of state. This is the most simplest form of equation of state. Actually, we have more. In oil reservoir engineering, we have Peng, Robinson, we have so many equations we have that we are using in 2020. You got the idea for the equation of state? That it is the relationship between pressure, volume, and temperature. In fact, we check the effect of one on the others. Okay, this is the first thing. Okay, then as we all know that we always have heard about the PV NRT. PV is equal to NRT. This is, we call it the ideal gas law. We don't say like it's a real gas law. The real gas actually behave a bit different than the ideal one. Ideal gas law is the one which we talk about this at standard condition or the atmospheric conditions that we have at the surface. So we can apply this equation when we have a situation like here. But when we talk about the reservoirs, the real reservoirs, the reservoirs are deep. Okay, they are quite deep, let's say 1000 meter, 2000 meter, 3000 meter, they are quite deep. And they are under high pressure, high temperature. We don't have 30 degree or 40 degree there in the reservoir. We have 80, 90 or 100 degree centigrade there. Pressure is not atmospheric, which we have at the surface, which is 14.7 psi. We are dealing mostly with more than 1500 psi, 200, 2000 psi, sometimes 5000 psi, sometimes 6000 psi. So very high pressure. We have very high pressure, we have very high temperature. In such conditions, this equation, PV NRT does not work. For example, you have pressure 2000 psi, you have temperature, let's say 100 degrees centigrade, and you want to find the volume, it will give you incorrect volume. Because this equation is used for just standard condition, not the real conditions, which are, let's say 4000 psi and or 100 degrees centigrade. You need a correction factor for the volume. So Z factor actually jumps in here. Okay, Z factor. So result from ideal gas law, but includes correction factor for P greater than the atmospheric. So if the pressure is above the atmospheric, this equation will not work. It will not give us the right volume based on the pressure and temperature. We have to use the Z factor in. So the new equation will become PV is equal to Z and RT. We have to find out this one, Z and RT. Okay, because the real gas behaves different under high pressure and temperature than the ideal gas. Ideal gas is the one which we say, which is at the surface. And the real gas is the one which is in the reservoir, which has high pressure and high temperature. So this behaves in a different way. This Z factor depends on the composition, temperature, and pressure, and so on. And we have some correlation. Most famous is Standing and Katz correlation. And we have to find out using this pseudo-reduced pressure and temperature. We will do that after this lecture. I will give you one question, homework, to do this Z factor calculation, which is available in the book of Tariq Ahmed using this one. I will talk about it, how we can find the pseudo-reduced pressure and pseudo-reduced temperature. These lines show the pseudo-reduced temperature. This one. This is one of the important calculations that we do in reservoir engineering using this one. So we will talk about it, how we do that in finding the Z factor. So Z factor actually is the correction factor. How you can define the Z factor is basically the correction factor for equation of state. Purpose is to pressure is deviated from the normal under high pressure, high temperature. This equation, as I said, will not give us the exact value. It will give us the wrong value. So we have to use this Z and RT, which relates the reservoir volume to the surface volume. Okay, reservoir volume may be more, surface volume will be less. So this Z actually will correct that problem that we are facing in the Z factor. And we have some equations that we will use in the later stage. Now we have the gas formation volume factor. Gas formation volume in barrels at reservoir condition occupied by 1 standard cubic feet of gas. Derived from the compressibility equation of state, relates gas properties measured at surface to properties of gas in the reservoir measured in lab. Okay. Now let me start the whiteboard and explain you what's going on here in this one. Okay, let's suppose we have a gas reservoir. We have the wet gas reservoir. It means gas plus oil traces. So what it has actually, let's say this is the gas. Now this gas has a small traces of oil inside it. It's mixed. Okay. So basically it's a gas reservoir, but it has some traces of oil. Yeah. Now you as a drilling engineer, you can jump in here, you start producing this well. Yeah. Okay. Remember pressure here is 2000 psi, temperature is 100 degrees centigrade. This is the situation. Now what happened, this block which we have is coming out. At the surface. As this block is coming out at the surface, its volume will shrink. It's the same this one, but its volume will shrink. The question, why? The question is, we had the gas coming out, okay, but as it goes up, the gas volume is shrinking, is reducing. This is the gas formation volume factor. Okay, we have to find out how much volume is reducing. Okay, but the very good question comes here, why this volume is reducing? Anyone can answer me? I have the answer, but I want to know from you. Okay, as I said, in the initial conditions, we have this gas reservoir, wet gas reservoir. It has the oil traces inside it. So here we have the oil traces also. It has a small amount of oil mixed with it. Like you have cola, it has a lot of sugar mixed with it. So when the now pressure here is 2000 psi, and as we are going up, the pressure is also declining. Pressure probably here is 1000 psi. As you know, and I know from the ideal gas law or the real gas law, if the pressure is changing, reducing, the volume will increase. Okay, I write it here for you. Pressure decrease, volume increase. Okay, but here volume is decreasing. Here pressure is decreasing, volume is also decreasing. Why? It is because previously this volume here at this point, the mixture was oil plus gas. As the pressure is declining, the oil is coming out, making a separate phase. Okay, it becomes like this. So now gas is separated. This is the oil and this is the gas. So as the reservoir volume fluid, which is coming out inside the well, because of the pressure decline, gas and oil are separating to each other. And when they are separating, this gas volume is reduced, is shrinked, and oil is coming out and makes a separate phase. So in the borehole, basically we are dealing with two different phases. Inside the reservoir, it was one. So because pressure is declining, the volume has reduced. Now volume is different inside the well. So this connection, the reduction in volume from the reservoir to the surface, we put it in the term, we call it a formation volume factor, which actually relates the reservoir volume with the surface volume. And of course, it changes after the bubble point, when the first drop of bubble, or dew point, when the first drop of dew coming out. Got an idea? If not, I can repeat it.
No, sir, can you repeat that?
Yeah, okay. Okay, we are discussing the formation volume factor. Our idea here is to discuss the formation volume factor. Volume factor. What the formation volume factor does, actually relates the volume in reservoir versus surface. That's the formation volume factor definition. As I said, the volume in reservoir is, we are talking about this one. And what is it here? Reservoir fluid, it is the mainstream is gas, but it has some small amount of, let's say, oil in it. Same kind of behavior when you see cola, you have color inside it. You have a water, and let's say you put sharbat in it. Let's say, sharbat, let's say, or any juice, that is sunquick. You add sunquick in water. Okay, so sunquick actually is the water plus sunquick. You have two items. Okay, that's why the volume is more, because now you have two items, sunquick as well as water. Now what is happening because of the pressure decline? Because this, after we drill the well, we want to take out this fluid to the surface. When this fluid moves from this reservoir, moving from this place towards this place, the pressure is declining. In the reservoir, pressure is 2000, but as it reaches to the surface, the pressure is declining. Because of the pressure decline, whatever the liquid was inside this gas is coming out. Okay, and making a separate phase. So when it comes out, the gas becomes small. Because gas was swelling because there was oil inside it. So after some time, when the pressure declines, the oil comes out of it, and gas becomes separate, oil becomes separate, and the volume then both will take with the smaller one. Total volume will be the same, but the gas volume will be the smaller one, because there was oil before. Here it has the oil before, but now it does not have the oil. That's the difference. Okay, let me share with you one video about it, so maybe you understand from that. Okay, I don't have it here, but I will put it after that one. Okay, so basically, as I said, we have the volume in the reservoir is different than at the surface. Volume in reservoir is more, because whether we are talking about the gas as a major reservoir, there's the oil traces inside it. So when the pressure declines, that oil comes out and gas becomes smaller. The gas volume becomes smaller. Not the amount of gas, the volume of gas, because before it there was oil mixed in it, and later on the oil was removed because the pressure declined. The oil comes out, and it happens at the bubble point. But I can show you the video of bubble point. at it, what is happening here? We have a liquid here. This is not the fluid or liquid here, this white one. This is the magnetic stirrer. It is moving continuously, keeping it mixing, keeping the fluid in the same phase. So we have one phase here, which is liquid. Okay. Now what is happening here? We will reduce its pressure. We will drop its pressure. When the pressure drop, whatever the gas or air bubbles are inside it, they will come out, and you will see. First, the vapors are formed. Here you can see the pressure drop. Here the bubble comes in. Okay. This is the bubble point pressure. Pressure at which the first bubble shows up here is called the bubble point. We have the magnetic stirrer moving, constant temperature, and the pressure we will decline it. We have a liquid here, and we want to drop the pressure, and we want to see exactly at what point the first gas comes out. Because when the first gas comes out, the volume will decline. Volume of this liquid decline. That is the formation volume factor. How much volume will decline? This is the formation volume. And the pressure at which the first bubble comes out is the pressure. Bubble point pressure. There you see what we are doing now. We are dropping the pressure. Here you can see the first bubble here. Got the idea of bubble point now? Okay. Now let's move ahead. The formation volume factor. So, as I said, you have to just spend some time with it. You will get the idea what exactly I'm trying to talk. And this lecture is also recording, so you can go and repeat what exactly I'm trying to talk. Also, you can take help from YouTube and books also at the same time. And if you still face problem in really getting a concept of what is this, we can talk about it again. Okay, gas expansion factor is actually the opposite of formation volume factor. In the formation volume factor, the gas shrinks. In expansion, it expands from the reservoir condition to the standard conditions. So we have expansion factor, and it's actually the opposite of the formation volume factor. We talk about it. It's different. Here you can see if the pressure, for example, is declining, the expansion gas is expanding, and the formation volume factor, this is the formation volume factor, is going in opposite direction. Usually we say they are opposite of each other. Okay, gas will expand and formation volume factor will decline. That's what we say in general. Okay, then we have another one, is the gas compressibility. In reservoir, the gas is again as a very highly compressible gas. It changes it takes the shape of the container. So we'll talk about it now. I have a very nice.
Hello, welcome to Mr. Rule Science Classroom. This is a demonstration in solids, liquids.
The gas is compressible, and when you compress the gas, it can create a lot of pressure because the molecules are compressed.
And gases, specifically gases, is a demonstration in air, pressure, air which is a gas. There is gas that remains above the water, filling the space or volume between this red line where the water stops and here where the cap is sealed on the top. This is filled with air, which is a gas. Gases are compressible, more so than liquids and much more so than solids. What I'm going to do next is to tighten this vise, and what's going to happen is the bottle will deform but also its volume will shrink, the water will creep up past the line, and it will compress the gas towards the top. See the water level rise past the red line. The shape of the bottle is changing underneath, but while the shape remains the same at the top, it becomes pretty obvious that there is the space that the air had occupied, which is a gas, is being taken up by the water. Now that can only mean that either the gas is mixing with the water, which it is not, or that the gas is being compressed into a smaller space. Its volume is...
So what he's doing, he's compressing the gas. Okay, there's a gas inside this bottle, air you can say, and he's compressing the bottle as much as possible to see how much gas can be compressed and see its effect on the pressure.
Decreasing. That gas is occupying a much smaller space, and without increasing or decreasing the temperature, that can only mean that there must be an increase in pressure. To check for that, I'm going to try to take this cap off. I'm going to try to do it very quickly for a sudden release of pressure. Here we go. The gas pressure demo showing that a decrease in volume causes an increase in pressure. This time I want you to ask yourself, what causes all that liquid water to be ejected from the bottle in the process? Think about that as you're watching it a second time. Here we go. Volume.
So you can see how much gas was occupying the volume, or the air here in this case. So it was from here and here. What he did later on, he compressed it as much as possible. So he compressed. Now you see the volume is declining. He compressed it more, declining. So as much as possible he could decline. So as the volume of the gas is decreased, then
into a smaller space, its volume is decreasing. That gas is occupying a much smaller space, and without increasing or decreasing the temperature, that can only mean that there must be an increase in pressure. To check for that, I'm going to try to take this cap off. I'm going to try to do it very quickly for a sudden release of pressure. Here we go. Of the gas pressure demo showing that a decrease in volume causes an increase.
Imagine this was the pressure demonstration in a single bottle.
Hello, welcome to
reservoir pressures, 2000 psi, 3000 psi. So they are actually very, very high.
Compressed into a smaller space in pressure.
How much gas can be compressible is actually given in this equation, which is the function of which is the function of pressure. Okay, gas compressibilities are very much higher than the oil compressibilities. So if the gas is compressed, its pressure will increase. That's the one. Viscosity, you all know that generally decrease with decreasing pressure. Okay, as the pressure declines, the viscosity also declines of the gas. Then densities, you all know viscosity, specific gravity, you know all of them. Then we have one concept, moles, number of moles. Anyone can describe what is the number of moles? What is mole? 1 mole. In chemistry, probably you have heard, maybe fluid mechanics, maybe so on. Anyone? Can you hear me?
It is the unit of measurement for the amount of, like, let's say, substance.
Amount of, you can say the number of particles in a gas.
Yes, particles.
If you remember Avogadro's law, 6.02 into 10 power 23. So number of 1 mole is actually the number of particles. How many particles is the 6.02? Actually, we use this also in gas calculations, in oil and reservoir, because as I said, reservoir engineering is all about calculation. It's all about visualization, imagination, calculation, and that's it. Drilling and production are different. They are physically, you can go and play with it. Reservoir, you cannot touch it. All you have to do is to play with those equations, play with those concepts, and see how they work. So I will now show you a very nice video they made about the moles.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists look at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is